Remember, we use a predicted value u star which is obtained by our backward difference, so u and I minus delta t over delta x e I plus 1 minus ei, both at time n. And then our correction step, un plus 1 at I, the final value for each iteration, 1/2 of u and I plus u star I minus delta t over delta x, and here we have e star at I minus e star at I minus 1. So we have, this is going to be your step 3 of the new assignment. This one, you have another requirement for stability, which is, again, that delta t over delta x has to be smaller than 1 over the absolute value of the solution.
What's E star?
E star, once you get U star, you can calculate E star. Basically, it's, yeah. So all of these depend on the previous step. Okay, you already visualize how this goes in the code, right? So now, the beam warming method. Now, this is beam warming implicit method, okay? So this is going to be a little bit more challenging, and this one is not to be confused with the beam. This is another beam and warming method. Is different than different from the explicit second order upwind beam and warming method that we discussed for the linear equation. This is another one, and we'll develop this. It's going to take a little while, so bear with me. It's going to give you, again, we're going to start from the Taylor expansion. So I'm going to write these now, just to make it more clear. I'm going to write these like this: u of x at t plus delta t. We're going to incorporate the indices in a little while, but first I'm going to write it like this: equals u of x and t plus du dt at x and t times delta t plus the second derivative of u with respect to t, again at x and t, delta t squared over 2, plus some higher order terms of order delta t cubed in this case. And now I'm going to write this other Taylor expansion. U of x and t is equal to u of x and t plus delta t, and now minus du dt at x t plus delta t multiplied by delta t plus second order derivative of u with respect to t. Again, this is a different point, x t plus delta t, and we have delta t squared over 2 plus order delta t cubed. So we're going to take these and subtract the second one from the first. And when we do that, notice we're going to subtract this equation from this equation. So I'm going to have this term on the left-hand side, and again another one of these on the right-hand side, but this one's going to have a minus sign. So I'm going to move it to the other side, and I'm going to have two of these. Again here, when I subtract this one, it has minus sign on the right, and I move it to the left to have 2 ux comma t. And these terms here have plus du dt x comma t delta t, and this other one, when I subtract it, I have a plus, but note that I can't combine these two because they are at different points. So this one is du dt, they are evaluated at different points. This one is at x, t plus delta t. And I still have the second order terms. Write the second order terms here. Second order derivative du dt squared at x comma t delta t squared over 2 plus, minus. This one is a minus. When I subtract this equation, this one becomes a minus. X comma t plus delta t, again multiplied by delta t squared over 2, and I have all my order delta cube terms. Now, when I have it like this, I can associate the appropriate indices for this. And whenever I have t plus delta t, that's n plus 1. Whenever I have t, that's at index n. You agree? So that's what we're going to do. We're going to write this is going to be, I can divide over by the 2, but this one is going to be u at n plus 1. Use the point I everywhere. This one is going to be un. The same for these derivatives. This is going to be du dt at n and I. This one's going to be du dt at n plus 1 and I. You agree? Okay, so this is what I'm going to write next in terms of indices, this same equation. Okay. We have u at n plus 1. I've divided over by the 2 equals u n I. So I'm going to have a 1/2 here for these other terms, which have all the derivatives. Du dt at n and I. And I had plus du dt at n plus 1 and I. And all of this was multiplied by delta t, plus I had the second order derivatives, again evaluated at n and I, minus, this is the only minus that remained, du second derivative, du dt at n plus 1 and I. And all of this was multiplied by delta t squared over 2. And again, we had higher order terms of third order. So now we're going to substitute the second order derivative by a Taylor expansion, du dt at n and I plus d dt of the second order at n and second order derivative at n and I times delta t.
Oh, sorry, should there be an extra half on the last
So this is a 4. Okay, so this is delta t plus order delta t squared. Now, when I put this back in here, notice that this term, which has a delta t, when multiplied by the delta t half, it's going to be a delta t third that I can just bundle up with all my higher order terms. And so it doesn't matter, right? So we're going to get un plus 1I equals to uni plus okay, so this one, this higher order term disappears because it's multiplied by delta t squared, and this one simply cancels this one out, so all of this term is 0. Okay, so we're just left with the first one, which is 1/2 of du dt at ni plus du dt at n plus 1 I multiplied by delta t, and everything else was bundled together in this order delta t cube.
Why does the first order du dt cancel the second order du?
This one, this whole term is going to be 0. Okay, this whole term I'm going to cancel it out. How? I replace this one by this by this part here, right?
Mm-hmm.
When I do this, oh, okay, I see what you're saying. I see what you're saying. Okay. Yes, you're right. You're right. I made a mistake there in my explanation. So I actually made a mistake on here because this one should be second order. So the function is the second order derivative, and I'm doing a Taylor expansion of that function. So I was a mistake in my writing here of this. And so now you see this one cancels out with that. This one cancels out with that. And the other term is order delta t multiplied by delta t squared is all bundled up with my higher order terms. And so the whole thing disappears. And that's how I'm left with that. So we have our final here. Well, now all I need to do is, so let's see, I have the whole thing correct, and all we need to do now is deal with these du dt's. But we have our Burgers equation. I'm waiting for my pen to appear. Oh, here. For which du dt is equal to minus dE dx. So I'm going to rewrite it in this form just to show the order of the whole scheme, which is actually just second order, because this is the whole scheme. Although this is not the way you program it, it illustrates the order. We still have the 1/2 minus 1/2 and dE dx at n So we replace the du dt by dE dx. And I wanted to illustrate here that this scheme is order delta t squared when I divide over by delta t. And now, so the important thing is that in the previous schemes that were just presented, that were explicit, the nonlinear term was applied at the known time level n. Remember we wrote E, there was always this term, this flex term E had a time level n, which means it's known for the next time level when you need to calculate the next time level. So it resulted in a formulation that was linear, despite the fact that the actual PDE is nonlinear. The formulation of the difference equation was linear by using the flux values at the previous time step, the values of E at n. Here, we are stuck because we have some terms that are at n plus 1. So this term indicates that this is a implicit method because of the nonlinearity, okay? Because this n plus 1 has to combine with this other n plus 1 here. So we need to do a little bit more work. Basically, we want to incorporate a linearization procedure to be able to work with this. And we're going to consider a Taylor expansion of E. So let's write E at t plus delta t is equal to E at t plus dE dt delta t plus order delta t squared. And do you remember the E dt from our the fact that E is a function of u? We can write it as dE du times du dt delta t plus order delta t squared. And in terms of indices, this indicates that E at n plus 1 is equal to E at n plus dE du, which is the Jacobian, and we have du dt, so un plus 1 minus un divided by delta t, all multiplied by delta t, plus order delta t squared. So dE du is the Jacobian for this equation. At every point, it doesn't matter, they're all at the same point, so I didn't write the point. It doesn't matter, it's just a time level. So dE du is the Jacobian A. Which for this case, for this equation, is equal to u. Just for Burgers equation, but we write it like this because we want to have a general method. So now, we're going to take derivative of this equation. So we're going to get dE dx, and then when we have dE dx, we can put it inside this here. Okay? That's what we're going to do next. So take dE dx, d dx of the previous equation, and we get dE dx at n plus 1 is equal to dE dx at n plus d dx of, we had in there dE du, which is the Jacobian A, and we had un plus 1 minus un. And that's all. So now we're going to use this and substitute back in the equation that we just had that had the dE dx's. The difference equation that had the EDX, and the two time levels, and we can get un plus 1 minus un divided by delta t, we didn't touch that, minus 1/2, and here we had right, so we were worried about this point that was the EDX at n plus 1. That's where I'm going to put that. So we still have the EDX at n and I, and the other term I can incorporate this, the EDX. Of course, it's the same, ni plus TDX of A times un plus 1 minus un. And this closes there. Right. Okay. So of course now we can write u at n plus 1. So all of these are at I. Look at the i's here. And we can isolate, this is the next time level, but we still have a un plus 1 over here. So we still got to do a little bit more work. This is of course 2 d dx and I, and for this we use second order central difference. Let's do this one. d dx of A un plus 1 at I minus un at I. So we use central difference with respect to x here. So it's, this step is going to be 2 delta x for the central difference. And we're going to use, we're going to apply this to the first product and then to the second product, okay? And the first one has un plus 1, and the second one is going to have un. So, and we're going to also consider A at time n, so we're going to write A, so this is for the first term, okay, for the first term, for this product over here, at I. A second order central difference will require points at I plus 1 and I minus 1. So it is A at I plus 1 and U at I plus 1 minus A at I minus 1, U I minus 1. And what are the time levels? Well, for U, this guy over here, so n plus 1. And for A, we're going to use the value at the known time level n. This is the first product, and so we need the second product minus, it's got a minus over 2 delta x. The second product, again, is going to have It's the same point I, so A at I plus 1, U I plus 1 minus A at I minus 1, U I minus 1. And what are the time levels? Well, U is evaluated at n, and we keep using so this is basically the approach is to use the value of the Jacobian at the known time level n. This is actually has a name. It's called, use the lagging value of the Jacobian, the lagging value, the value of the previous time level. So we can rearrange now this whole system so it looks like a tridiagonal system. And I'm going to write it again, basically just plugging this in this equation. But I'm going to clear the slide so it's all very clear in just one slide, the whole thing. So now we rearrange so that it's represented as a tridiagonal system. So all of the terms that involve un plus 1 will go on the left-hand side of the equation. And what were those terms? We had, of course, the un plus 1 that we had from the beginning, and we get two more terms that are multiplied by a that have un plus 1. Those will move to the left-hand side. One of them, so two of them have a's multiplying. One is this delta t we had when we applied the central difference, we get a 1/2, but the whole thing was also multiplied by 1/2 delta t. So it's 1/4. So delta t divided by 4 delta x, our exponent. And this is a. N I minus 1, U n plus 1 I minus 1. And we have one term which is simply U n plus 1 at I. Then we have another term which is the same coefficient for delta t divided by 4 delta x. And A at I plus 1 and U at I plus 1 n plus 1. So here's our three unknowns with their coefficients, and this is equal to u at ni minus 1/2 delta t over delta x. This is the terms with e at n, I plus 1, minus e at n, I minus 1. And we have the other two terms that have a, plus delta t over 4 delta x, a, I plus 1, u, I plus 1, both at n, minus a at I minus 1, u, I minus 1, both at n. So everything on the right hand side is known, and we have three unknowns on the left hand side, and you can see there that this consists in a linear system of equations with a tridiagonal coefficient matrix. So this is a second order scheme which is unconditionally stable. This is going to be your step 4 of the new assignment. As a second order scheme, remember all the higher order schemes, second order schemes that we've seen have some oscillations, so you can expect to see some of those oscillations. And you're going to have to find a way to solve a tridiagonal system and read the Python manuals. It's not, it's surprisingly easy. And
I'm not doing it.
I thought so. Yeah, you can do it in Python like everybody else if you want, or something else. Yeah, solving the linear system is something that is an additional difficulty. So as for the other second order methods, you will see some oscillations. Okay? The question is how it compares with the previous ones. So I'll end afterwards when we finish this class with a little bit more guidance about the assignment. Dispersion error, in other words, right? This is the dispersion error. Okay, so the scheme should be clear. I think, of course, whenever E appears, that is just the value of U times itself. This is just U n at I plus 1 multiplied by U n at I plus 1. So you can do that. Let me go back to write. Okay, so the practical module consists of doing this nonlinear convection. And remember, we this we introduced the last class. Our initial condition is going to be basically a traveling shock wave, a traveling shock. We have the value 1 and the value 0. And this is 2 and 4. So the value 1 is between 0 and 2. The value 0 is between 2 and 4. Okay, this is our initial, it's a traveling shock wave. So you want to investigate the propagation of this discontinuous function under the Inviscid Burgers equation with Lax-Friedrichs, Lax-Wendroff, MacCormack method, and the implicit beam warming, which we've seen. In addition, we're going to do, this is going to be step 5. Step 5 is going to be to investigate the effect of adding a damping term to the final difference. So what this means is we add on the right hand side a fourth order damping term. Which looks like this. D equals 2 minus E, this is a coefficient, and our difference equation is I plus 2 minus 4U at I plus 1 plus 6 UI minus 4 UI minus 1. So it's a 5-point formula plus U I minus 2. All of these at n. You can see that this is a consistent difference by the trick we discussed last class. 6 plus 1 plus 2, that's 8, minus 8, 0. So the sum of all the coefficients of this final difference equation is equal to 0, like it should be. So I want you to experiment with values of this damping coefficient epsilon between, let me write it, between 0 and 0.1 125. And also try some values just try a couple of values greater than 0.125 and see what happens. And then with the value of 0.1, experiment with different step sizes. And different Courant numbers. Delta t over delta x in this case. And so after you do steps 1, 2, 3, 4, and 5, the question is, which yields the best solution for the Burgers equation? Okay, everybody clear? It shouldn't be too hard, we hope. Okay, let me add some notes before we go. About this damping term. First of all, note that adding a fourth order damping does not, well, to a second order scheme does not alter the order of accuracy. Of the overall formulation. You can see that's not going to be a problem. Now, in the assignment, in the above formulation, we add this damping explicitly to the right-hand side of the equation. As a result, the stability of the scheme changes, and the stability in this case will require an upper limit on the value of the damping coefficient. Now, what is the whole purpose here? The purpose is to add the purpose of this damping coefficient is to reduce the oscillations that are associated with this higher order scheme. And if by adding it explicitly on the right hand side of the equation we have an upper limit on the value of the damping, it could be that this is not enough to damp out the oscillations. So that's something that one still needs to see if it works. It might work, it might require, to be able to damp the coefficients, you might have to require a damping that throws the scheme into an unstable regime, and then bad luck, right? So that remains to be investigated. So this value could be insufficient. Could be. We don't know. You will investigate to damp oscillations. A typical fourth order damping in 1D is this, has this form. This is the little e is for explicit because we're adding it in explicit form at the right hand side of the equation. Delta x to the fourth times the fourth derivative. This is the difference formula that we wrote in the previous slide. This is the explicit one. And this, you can see, can be easily now extended to higher dimensions when I write it this way. In higher dimensions, you could have delta x to the fourth times the fourth derivative with respect to x plus, say, delta y to the fourth plus the fourth derivative with respect to y, and so on. So you can see how this can be extended to higher dimensions. (2D, 3D, etc.) Probably not more than that. And so sometimes if because of if the point 2 above leads you to insufficient damping, one can add, then in that case we can add a second order implicit damping. We're not going to do this, but I'm just informing you that sometimes if the situation that I described in point number 2 happens, that is that the maximum, the upper value of the damping coefficient allowed by stability is not enough to dampen your oscillations, then you could add, in addition, a second order implicit damping. That means we're adding it to the left-hand side of the equation. So things are going to be at n plus 1, and it will have the form EI. Now the I is for implicit, and it's a second order one, so d2u dx squared. And you can approximate this again by central differences. Finally, we're not going to do all the analysis, but one can do a stability analysis. And this is what is required to identify this maximum value of the damping coefficient. And also, if you use this combination of explicit and implicit, you can get a maximum value of, and also the ratio between the explicit and implicit values, so that one can obtain basically a stable scheme that has enough damping to get rid of those oscillations. All of these things have been introduced to deal with solutions that have shocks, that have discontinuities, because we've seen how those lead to very dramatic oscillations. And this is basically, I'm going to call it damping for you to understand what's going on. But this is also called artificial diffusion, artificial viscosity. The artificial viscosity will be the value, right, of the this coefficient. And artificial diffusion is what we're doing to the equation. Artificial indicates that we're just, it doesn't respond to any physical diffusion. We're just adding it to our difference scheme to dampen the high frequency oscillations and get something that's more. So let's see, a typical value of this. Finally, let me just write that typically you can have EI required to be greater than 2EE for those cases. And that's all.